Good morning. While we wait for few more people to trickle in, there's a couple of housekeeping things that I want to get out of the way first. Um, Homework is going to be out soon. It's taking me a bit longer since the order in which I'm covering topics is a bit different from how it's been done so far. But um, Friday, I think, tentatively, I'll put it out. Examples for some of the operations that were introduced so far. I've put them up on UB Learns. I've also added a document with a couple of links to class. Um, and that core class's material is what the fall offering was largely based on. So there's a lot of detailed explanations in there, which I can't really go into that much depth when I'm covering topics. So there's YouTube links. Um, and I've tried to list what the relevant videos from those playlists are, but use your best judgment. Um, that should help for operations that aren't very straightforward. Um, I'm still holding off on quizzes because I'm just waiting for enrollment to finish completely for everyone. So once that's squared away, I'm hoping by the end of the week, starting next week, you can expect in-class quizzes to start. Um, for the homework, during the first class, I said that I did not want Colab links, but that's a policy that I used to follow before ChatGPT was a thing. So I think in the interest of being able to just track how you progress through homework, Colab would probably be the best way to go about it, since it has edit history that I will also be able to see. Um, so I'll update the syllabus about that, and the um, problem statement for the homework will also have instructions on um, whatever setup you would have to do or environment related stuff. Um, yeah. Uh, so today we're going to be continuing with image processing, which is what we talked about last class. We'll be talking about the Fourier transform today. This one's kind of a doozy, and it's tricky to explain. I had put in a link to the video by 3 Blue 1 Brown at the end of last class slides. If you haven't watched that, I would recommend watching it after class, just so that really cements the explanation, because it's a bit hard to develop intuition for it. So the Fourier transform is something that's very useful, not just in image processing, but for anything that can be modeled as a signal. And what do signals have? We're able to think of signals in terms of frequency, and by being able to separate out composite signals that have more than one frequency, we're able to tell more about the signal. So what do I mean by a composite frequency? An example is if you play piano or guitar or any instrument and you play a chord, that's a combination of notes, and each of those notes has a frequency associated with it. Um, this example here shows the addition of an A and a D note, and on their own, they're pretty straightforward sinusoidal signals. But when you put them together, it becomes complex, and you don't have a way to identify the individual signals from that. So the Fourier transform lets us do that. And before we actually talk about the transform itself, another visualization of how complexity further increases the more component frequencies you have that are contributing to it. This is from, I believe, lecture 2, where I had pulled out the middle row of an image and plotted its intensity. And thinking of pixel values and how they repeat in terms of frequency is a bit trickier, but it will make sense eventually. So when we look at this particular signal, it's not hard to guess what the frequency of the signal would be if you pick a certain time range and just count how many peaks are in it, right? We're able to do that because it's a single frequency. There's nothing mixed with it. So that peak counting method is not going to be valid once you add in another signal. So another representation for the same signal is you take an arbitrary length that you would know. So in this case, it's 4.5 seconds. And then you convert it to the polar form by wrapping it around the center. And you then have a vector that follows the amplitude of the signal. But instead of going in a straight line, it rotates around the center. Um, One of the unknowns when we're trying to do it like this is how tightly do you wind it around the center. That is a choice for us to make. So there's this interactive visualization that someone made. And I'm going to pull that up and let's play with it a little bit and see if we can find a pattern. So we have here, tricky. Okay. So at the moment, there's one signal, which has a frequency of 3 cycles per second and an amplitude of 1, and it's shifted above the x-axis by 1, because if the shift was 0, then this would lie on the x-axis and peaks would be above and troughs would be below the axis. So it's just easier to think about it initially, but it generalizes regardless of shift. So when we vary the frequency, this is what angle maps to one cycle, basically. How many radians are covered in one cycle is another way of thinking of the winding frequency. So we can keep varying that and we'll see a bunch of patterns. Now, if you think of what is being wound around the center as metal wire that has mass, then you can calculate the center of mass of this entire arrangement. And that's what's being plotted on the other side over here, the position of the center of mass. So something interesting happens when we get to the actual frequency, if I'm able to get there. Yeah, so I'm at 3 now, and the center of mass of that coiled wire has shifted by a lot to the right. And that is something that we can track, the position of that center of mass. We get a peak corresponding to where the frequency matches what the actual frequency of the signal is. And the same thing works if you add in another signal. Um, and I'll set this frequency to, yeah, that should work. And I'll close this back up. So now we have a more complex signal. And going over the frequencies, there's two peaks now. One of them corresponds to 3, and the other one to whatever I set it, I think it was 2.73. And you can keep adding signals, and this will still be true. So just one more of these for good measure. We have a third peak over there now. So how do we have the trend now, we know what we're looking for. How would we mathematically calculate that center of mass? It's an area under the curve of the position of the center of mass. So since it's area under the curve, that means we're going to be doing an integral. G of t is the composite function whose Fourier transform we want to find. We multiply that by a term that's derived from Euler's formula. And since what we're trying to find is an angle that maps to a cycle, the x is what we're interested in. And we can derive that from angular frequency, which is what we're setting when we change this, what the winding frequency was. And angular frequency is radians per cycle. Your normal frequency is cycles per second. So you're going from time to angle. And multiplying that by seconds would cancel out the unit, and that leaves you with just an angle. So the 2 pi comes from 2 pi radians, which represents a whole rotation around it. And this gives us the position of the center of mass. So a couple of examples again, like we saw. This is for a composite of 2 and 3 hertz, which is cycles per second. But images, while they can be thought of signals, they're discrete, and the transform that we just looked at, that was an integral over a continuous function. So we need to adapt that for the discrete and 2D case. So the discrete equivalent is relatively similar. It's a similar term. There's still the Euler's formula term, where instead of frequency times time, we now have indices that iterate over pixel values in both the target signal and the input, and then you divide that by the number of samples that you have, which in an image case is the number of pixels. Why do we care about this and about thinking of images in terms of frequency? When you have the ability to identify all the constituent frequencies in a composite signal, you also have the ability to get rid of some frequencies. So if you're thinking of sound and you're in the studio, you're a producer, you made a beat, and there's this, you're hi-hats sound really tinny. So you want to get rid of some of the higher frequencies. You can build what's called the low pass filter and apply it to the signal. So that will get rid of the, say, 11,000 hertz artifacts that you have in there that you don't want. What does this look like for an image? So the magnitude spectrum is similar to the polar form for a one-dimensional signal that we saw. This is the farther away from the center that you get, it's higher frequencies. And this is two-dimensional since our image is two-dimensional. When you set a limit of how high you want the frequencies to go and discard everything above that, that gets rid of what's called high frequency noise. And it doesn't look like much has changed between the two images, right? It's got marginally darker, but if you do the converse operation of this, that would be a high pass filter, which gets rid of low frequencies or allows high frequencies through. It lets high frequencies pass the filter. And when you apply this to the image, what you get is the pixel values that repeat really quickly. And that corresponds to edges. So we're able to extract edges using the frequency domain. We saw how to do it using derivatives. This is another way to do the same thing. If we, now when we talk about to put image compression into context, so with audio, there's different streaming qualities that we have, and that's largely dictated by the bit rate, which is how much information you're hearing per second. So if you have a whole bunch of frequencies that all need to be in the signal, then you'll need more bits to represent that. You can discard a few of the ones that don't really contribute much to the signal but are still present. So how compression here would work is we know the amplitude for each and every frequency based on the pixel intensity. And we just threshold this image to discard ones that are not contributing much. So here I set the threshold to 0.02% of the maximum amplitude in the magnitude spectrum. And that got rid of everything that was below that threshold. Image still looks pretty similar, but we discarded a bunch of information. Changing the threshold, this is 0.1% now. We've lost a lot more frequencies that weren't contributing much. Image still looks relatively similar. It hasn't degraded too much, but we keep doing this and it gets a lot worse. Another application. So in here, I have an image into which I embedded a watermark. Any guesses on how I could, yeah. This magnitude spectrum, it's frequencies and how much they're contributing. So if I plot this in, no, it's not, it doesn't correspond to pixel location. So for each pixel, how often it repeats. Um, if there's a pixel value that repeats a lot in this region, you go from, say, uh, or in this particular region, there's some texture, which you could think of a little bit as a checkerboard of, say, two shades of gray. Like you have the value 20 followed by 22, followed by 20, followed by 22. So that's a pattern. And it has a very rapid rate at which that pixel intensity value repeats. But if you're going in a region that's smoother, then the variation in pixel values will be more gradual. Um, so let me think of how to represent that. So if I'm going from bright, this is dark, then I have a value, let's say 200, 198, 195, 190, 187, and this keeps decreasing. And then after that, it starts getting brighter again, and then you see a 190 at this point, maybe. So that's how long the cycle is, however many pixels are in between. So this would be a low frequency component. And the opposite of that would be when you have texture and rapidly changing values. So it's doing 200, 202, and yeah, 202, 201, 202, 201. So here you have that cycle with just one pixel in between. So this is a shorter cycle length. And instead of the time axis that we had for a 1D signal, here we have a number of pixels basically. Because if you extract a column or a row, then that's what you plot, right? The intensity. So 200, you went down to 198, went further down to 195, further down to 190. So this is the one-dimensional signal for one vector. And then we apply the same polar, what we use is the fast Fourier transform, which is different, but it's derived from this principle. And when you try to unmix it, you'll get frequencies that describe how often these pixel values repeat. And in the magnitude spectrum, it's the farther away you get, this is higher frequencies. So if you have a pixel, these cycles that have short cycle lengths and repeat fast would be towards this end or around there. And the ones like this, where you have that big of a repetition, would be closer towards here. And the how bright or dark they are in this magnitude spectrum has to do with how long that sequence is or how many times it shows up rather than how often. As for pixel location, this the angle here would correspond to where in the image it is, but that's not a trivial mapping to say that, oh, that region is in the top right corner. Okay, so going to okay, this was the signal that I got for one row from the image, right? And it's a one-dimensional signal. So I would do the FFT for this to get what the frequencies are. And I need to be able to represent it in a way that I'm also able to do the same thing for every other row and retain the information for every row in the image. So if it's one dimensional, I would have to um, combine it all into one vector, basically. Yeah. I mean, you have to do it for the whole image, and that it has to capture both the relation for a row and a column, right? Because there's patterns that show up both vertically and horizontally, and we need all of that. And um, it should still contain all the information from the original, because eventually we want to be able to do the inverse Fourier transform, and that gives us back the original image. So um, if it's just one dimensional, you wouldn't be able to represent coordinates and pixel values. So this still encodes that information, but radially rather than Cartesian. Um, yeah, so any other questions on what's going on over here? Does this does at least the filtering part make sense? Fourier transform itself, how you get to the image and what it means, it takes a while to wrap your head around it. So I would recommend playing with it in code. That's really the best way to have it make sense. This series of operations, any questions? Okay, just to recap really quick, we have an image, we calculate the discrete Fourier transform, um, which gives us a representation of all the frequencies with which pixel values repeat, and angle going around the center encodes position information. Um, Amplitude indicates how often that pattern repeats. We can then do things to the frequency domain image, which is what the magnitude spectrum is, and then invert the Fourier transform to get back the Cartesian domain image. So we talked about compression. Okay, watermark. Um, Assuming you also have the original image that doesn't have the watermark, how would you get rid of the watermark from this? It's the same principle, more or less. Okay, let's do it step by step. I have two images. Um, One of them has a watermark, one of them doesn't. How do I find the difference between them? Okay, and how do you see the difference? Right, yeah, so um, if th- I have a bunch of pixel values, so three, whatever, and then I have another one that has pixels corresponding to a watermark. These regions, and then these are two 2D matrices. So if I just subtract this and look at the absolute difference, so if the watermark here, if it's brighter, then this region would be negative. But if it's darker and I subtract it from the original, then I'll be left with just this region, right? Uh, the problem with doing it directly in the image space is that the the intensities vary as the um, original image intensity varies, right? So I wouldn't get the exact watermark. I'd get a mask of the region that also includes the result of blending the watermark with the image. Um, and if I tried setting every pixel in that value to 0, then there's just going to be CSE 573 written in black over there. So that's no good. How do we figure out what the original intensity over there was without the watermark? Since we're talking about Fourier transforms, we the odds of us having to switch to frequency domain are pretty high, right? Since we're on that topic. Um, two images, one of them has the watermark, one doesn't. We now have, we apply FFT to both of them. And then if you subtract uh, the original one from the one with the watermark, it gives you just the watermark. And um, you can then subtract this from the image with the watermark, and that gives you the original. I think the order in which I've pasted them don't really make that evident, but that's what the script did. And you can do it the other way around. So the way I added the watermark in so that I could subtract it was by taking the FFT of just this image and then adding it to the original. And we're able to do it back and forth. Okay. Uh, does all of that make sense so far? More or less? Okay. Um, Next up, we're switching gears a little bit. This is a lot more visual, a lot more practical. We're doing less math. Um, and it's something that we've touched upon a little bit earlier, Gaussian pyramids. So this is something that came up when we first talked about scaling transform, and interpolation also came up. We already know how to blur images, so this is a way to tie all of that together to do something useful. When we downsample an image um, by half, simplest way to do it is just discard every alternate row and column. That gives us an image that isn't really great, kind of blocky looking. Um, Similar things happen when you have high resolution images with high frequency patterns in them, that when you downsample, you start seeing artifacts. You probably see this a lot when you try to take a picture of your computer. Um, it's even more pronounced when we're dealing with synthetic images. The jagged lines, what should be straight lines, look jagged, and they're, at least in the computer graphics side of the field, they call them jaggies, which I think is kind of funny. Um, the reason we see all of that is aliasing, and what aliasing is um, a result of the way that you sample a signal. So if you have a signal that is, say, 10 hertz, and what is sampling a signal? Sampling it is to pick amplitude values at certain intervals of the signal. So if your signal is changing faster than you're measuring it, then if you try to put together the information that you get from the sample, then odds are you're going to find something that doesn't make sense at all, or even worse, you get a wrong estimate of what the signal is. And that wrong estimate is called an alias. The way to avert that is make sure that whatever it is you're measuring, you measure it at least twice as fast as it changes. And that limit, the minimum sampling rate, is called the Nyquist rate. So how fast a signal changes when it's a composite signal is whatever your highest constituent frequency in that composite signal is. So you need to be sampling it twice as fast as that. One of the ways that this shows up is, and that we've probably seen pretty commonly, I thought I had, oh, I deleted that slide. I had a visualization for this, but um, if your shutter speed is uh, faster, if your shutter is open for a duration that's shorter than you need for a video, which is 1/30 seconds, then what ends up happening is that the wheel appears to turn backwards. Um, I will. Me actually. At a certain point, it seems to switch direction that it's spinning at, right? I had another visualization. Let me pull that up and put it in here. Um, yeah, let's go. Oh, it doesn't let me seek. It's a lot more uh, clear. So basically, interaction between the rate at which you're sampling the real world scene versus how quickly the actual scene is changing. And when the wheel starts spinning faster, then the camera is able to record the direction in which it's spinning seems to flip. And that's called the wagon wheel effect. You also see this sometimes with videos of a helicopter taking off. The RPM of the rotor blades matches the frequency at which images are being canceled. So the frame captured, the frame rate of the camera and helicopter blade RPM is matching. Same thing also happens that you must have seen videos of like a hummingbird flapping its wings, and it looks like it's just stationary, not flapping it. Um, this is when you have a high resolution video, you downsample it without any interpolation, or if you're recording something from a screen, you see these artifacts because the lattice of pixels that is on the screen versus how it gets mapped to your camera sensor. If they don't line up perfectly, then again, that's an example of poor sampling. To put that into perspective a little bit better, we take a checkerboard and we're measuring pixel value every X amount of pixels. And that X amount is small enough that we're getting uh, two samples. One is right at the start, one is about at the middle of one square on the checkerboard. And it's consistent in both directions. So you know you're always going to see two black, two white in both directions. And um, here in this pattern, the cycle starts at a black square, ends at a black square, starts at white, ends at white. So even in this case, the pattern we're still able to capture since we're measuring twice as often as it repeats. So it's a bit unintuitive when you look at it because the Nyquist rate says that we should be measuring at least twice as frequently as the pattern changes. And you could say that it changes with every square, but that's not the pattern that's repeating, but it's a component of the whole pattern, which is an entire cycle. Oh, I didn't have my laser pointer on. That's an entire cycle. Um, and we're still sampling twice per cycle. Bad sampling. So here we have one sample for every cycle. And when you plot out the intensities that you sampled with this frequency, you're just going to get all black. And you wouldn't even realize that the source from which we're sampling had any other information. Same thing goes for this case, even though it appears to be getting black and white initially, the cycle length with which we're sampling it is longer than um, half of a cycle in the checkerboard. So when you extend that, you end up getting black, white, white, and that's not what the actual pattern is. So when we're downsampling by a factor of 2, there's high frequencies. One of the ways that we're able to fix this, which we have talked about before, is by applying a Gaussian kernel to it. So you blur it and then discard half rows, half columns, and keep doing that. And the result is a lot smoother than not doing the Gaussian pre-filtering. One of the cool things, which we will get to in a second. So this sequence of operations, uh, blur, then subsample, blur, subsample, you keep doing that until you hit the limit of how many times you can divide it. And the good thing is that this is discrete, so you're eventually going to run out of pixels when you keep doing that. You get a Gaussian pyramid. So it's an image that is subsequent, consecutively downsampled by a factor of 2 until you run out of pixels to further discard. And then that collection of the original image with its downsampled versions is called a Gaussian pyramid. So you have an image and you have a bunch of representations of the same image of lower scale. Seems like redundant information when you have the full high quality image. Why do you need lower quality ones? Um, this idea was introduced in 1983 by Burton Adelson, and also with the name Gaussian pyramid, and also introduced in computer graphics, same principle, but it was called a MIPMAP by Williams in 1983. This is a precursor to a wavelet transform, which I will cover next class, tentatively. You put all of it together, and it takes 4/3 of the original amount of space. And the reason is that consecutively having something is a geometric series. Now, what do we do with it? Why does that help us? We can blend images when we have images taken from different viewpoints. They're going to be projected at different scales. If you're really close to the Eiffel Tower and really far from the Eiffel Tower, and you take pictures and you want to combine them, then you need to match the scale of both of them. So you do that by building Gaussian pyramids of both and finding where they match. So matching is an application that I'll demonstrate, but we'll go into implementing that after we talk about feature extraction, which will come up later. So talking about feature extraction, we want, so in short, all you need to know at the moment is that features are condensed versions of patterns that we have been trying to isolate using the Fourier transform. Features don't necessarily have to be extracted in the frequency domain, but they're basically something that describes structure within the image, little vectors, or using which you can then find similarity between two regions in an image. And those need to be scale invariant. So if you had the small, the close-up shot of the Eiffel Tower and you're standing really far and you have a zoomed out image, you should be able to extract patterns from both of those that scale along with changes in scale to the changes in scale of the images. So they shouldn't vary with scale. So also lets us analyze texture. estimate motion, and detect objects. Um, the object detection case is classically called template matching. So in this image, somewhere there's this guy, a snow leopard. Now, how do we measure similarity between a mask and an image? It's one of the two new operations we talked about last class. Yeah, correlation. So if I if I tried calculating the cross correlation for this image with this filter, what I get isn't really going to make sense because this template is a lot larger than it should be in the actual image. And we're able to tell that because I know that. But if it's a case where you're just given a template and you're trying to find something in an image and you don't know what the relationship between scale is, the way to do that would be to build a Gaussian pyramid. So you have multiple scale representations of the original image and then try to find the template um, in each of those. And that gives you a measure of similarity when you do the correlation at different scales. It's, you see that little bright dot at 1.25 scale? It also shows up at 1.5. It's a bit more diffuse. At scale 1, you don't really see it. Scale 2, you don't really see it either. So here, wherever, at whatever scale you get a maximum is where the template would fit, basically. And we're able to detect a region that corresponds to that template using this. Another instance, that there's a cat in here somewhere. Um, the only thing that we have to go off of is a pair of eyes. So we do the same thing again. And so the detection is in here. That's where it found the cat, at that region. And there should be, at some scale, a corresponding bright spot, but um, a bit harder to see. I believe it was at scale 3. Uh, I'm having a hard time seeing it in here. I don't have my glasses on. Oh, but regardless, it's there, and by looking for this image, the template, which is a blown up version of this at different scales, we're able to match it. So in this particular case, you would have observed that I was doubling scale instead of halving it. Um, Having it is definitely more efficient because when you're upsampling, you would end up using a lot more memory to convert these to arrays that you compare. So you're basically taking an image and adding 3 more copies of it, which is not the efficient way to go about it. The efficient way would have been to have the template at the original size of the image and vary the scale of the template higher and lower, and only downsample the image within which you're looking for the template. This being something that I whipped up really quick yesterday evening, I didn't get the chance to optimize it much. Yeah. That's all the concepts that I wanted to go over for today. In addition to that, there's these documents that I've added. So it's in the miscellaneous section on UV Learns. The cross product one was there earlier. I also added a couple of examples for some of the operations introduced. So converting Cartesian to homogeneous is just adding a 1 to the vector, which is loosely correlated to depth of the plane. Converting back to Cartesian, you divide by the W term. Examples of translation, rotation, scaling. And I think one of the one piece of intuition that might be missing for you guys is that this needs to be done for every pixel. So this example is taking in the coordinate of one point and applying whatever transform to it, whether it's translation or rotation. So that gives you a new address for the same pixel value, and that needs to be applied for every single pixel in the image to be able to rotate the whole thing. Yeah, so scaling, there's also an example of shearing in here. Similarly, for pixel transforms, there's brightness adjustment for grayscale, for color, an example of compositing. Histogram equalization, the only real math example is just calculating the CDF itself. And for linear filtering, which is cross correlation and convolution, the way you calculate it is pretty much the same, with the only difference being flipping the filter when you're doing convolution. So if you know how to do one of those, then you know how to do both of them. And the final thing is this, which is what I had mentioned initially, 3 playlists and some relevant topics that are covered in each of those. This should help fill in any holes in understanding. Yeah, that's it. Homework will be out soon. And quizzes start next week onwards. I'm not saying that there's definitely going to be a quiz next week, but just be prepared. Yeah, that's it. That's all I have for today. I can take questions if there's any. And if you have any like general feedback on what you want me to do more of or less of, either Piazza or right now, whatever you're comfortable with, let me know. In class. And I'll aim to structure them so they can be completed in like 15 minutes, 15, 20.
That one plot you were showing up there, I think it was the magnitude plot.
Yeah.
Like I just noticed it had like kind of like a cross in it.
Symmetric?
Yeah. Is
Yeah.
Like, I was just kind of trying to understand.
So
I saw there was a shadow that went like directly over his face, but it doesn't map directly to it. Like
no, because we're we're converting from like X and Y linear to a radial representation of the same coordinates, so it doesn't map directly to how exactly the coordinates FFT magnitude. um, Sorry, what time did you come in? Why would you ask me that? Like you, the purpose is that you get all of the material, right? So, uh, oh yeah, your enrollment, I saw it didn't go through yet, right? Okay, I can give you the code for Piazza access, but all the slides are on UV Learns. I'll just email them to you. Yeah, yeah. Um, yeah, I'm trying to find something that like maps, or it's not a linear relationship. This is the closest that I could find. It's again an angular frequency. This is a
So it's just a little bit difficult to kind of interpret if I just look at it.
yeah. The easiest things to take away from it is that higher frequencies are farther away.
Okay.
That's about it. Um, exact positions. I'll look it up and see if I can figure out something intuitive to uh, get a relation between the two.
Okay, thanks.
So, in the 2D graph that you mentioned,
Mm.
before converting it to the standard, what is the intensity? How do you get that?
Intensity is how bright any of these pixels are.
In case of RGB image, you can't find it, but you can convert it into U in that in that representation you can find the intensity.
Intensity of, so what I was telling you is pixel value in this is intensity of that particular frequency. So if you go back to, what was that? Did you have more questions or? Oh, okay, yeah. Okay. Yeah, so here, if I increase the amplitude and decrease this, a little bit janky. Then the value of the peaks is different, right? The magnitude. This one is lower, that one is higher. So if you do a heat map of that, similar to this one, so this corresponds to a higher intensity, right? So this was in normal image space, but the same, you can get the same
I'm just
plot
how to
from
get the intensity, like,
intensity of what?
intensity of pixel image.
So
It's
whatever
intensity
the pixel value is the intensity of light at that region. So,
yeah, in the RGB format you can't find it.
uh, oh, okay, I get it now. So you have an RGB
RGB
image,
image,
and so you need to know the contribution of the red channel, green channel, and blue channel
Maybe
to
I can
light.
convert it into that you saturation intensity.
Yeah, you can either convert it to that or convert it to grayscale and get the intensity. So it's,
Oh, converting RGB to grayscale will also give it correct.
yeah, because then the um, individual contribution of each wavelength gets like normalized, and it's a pretty well-known relation for how much each color contributes. Um, for red, I think a close approximation is like 0.26, and then green you take some other value. I'm not sure what the actual values are, um, but yeah, when you multiply each channel by its corresponding coefficient, then that normalizes for intensity before you convert it to grayscale. And then after that, I think you'll either have the same values in all three channels once you multiply them by those coefficients, or you average the three channels. It's one of the two.
Thank you.
Yeah. Well,